So the thing that makes this system relatively easy is that it is completely decoupled. This is completely decoupled. What that means is that you can think about each equation individually. You don't have to think about the other equation. And then you just combine the results into one vector as a solution of the system. So dx dt equaling x and x of 0 equaling x sub 0 means x is x sub 0 e to the t, right? That's going to have the correct initial value when t is 0, e to the 0 is 1, x0 times 1 is x0. And it does solve the differential equation. It's a function whose derivative is always itself. On the other hand, the dy dt equation, a little bit more complicated, but certainly still something you can do in your head. It's also exponential, but now the power of e is negative 2t because of the negative 2 right there. This has got the right initial value. When t is 0, e to the 0 is 1, y0 times 1 is y0. Also, if you differentiate this, you get negative 2 times itself. So if you put these things together in a vector, you could call that the unique solution of the IVP. You could write it as a point. There's nothing stopping you from writing it as a point. We, in this class, typically write it as a column vector because it's more convenient for the purposes of matrix multiplication. That's the reason why we write it as a column vector. Chapter 3, it's more convenient for the purpose of matrix multiplication. So we go ahead and write it, the solution. We're doing number 1 now. Combining these things, our textbook would write vector capital Y of t equals a certain formula. But I want to continue to get you used to flow notation, for example. And I typically use a capital phi when we're talking about a system of differential equations instead of just one scalar differential equation. We got a system or a vector differential equation. If I put the subscript, that's the initial condition here, vector capital Y0, where vector capital Y0 has components little x0, little y0 of t, then I'm treating it as a solution of the differential equation. I'm treating the vector y0 as fixed and treating t as the variable. That's the thing that we're most used to. The flow notation switches the perspective around and the notation a little bit, puts the t in a superscript, and puts the y0 as the function independent variable. You think of t as fixed and the initial condition as essentially your variable. There are reasons for that. You can write it as a vector just by putting these things in the components. x0 e to the t and y0 e to the negative 2t. That's good enough as an answer for part 1. And again, if you wrote it as a point with coordinates with parentheses, like a row vector, that's okay as well. But we're typically going to write it as a column vector. Again, because it's more convenient for the purpose of matrix multiplication. And let's actually relate this to a matrix multiplication. I could think of this vector as the sum of two vectors, x0 e to the t 0 plus 0 y0 e to the negative 2t. And I also could write that as the linear combination. I can pull the scalars out in front. x0 times e to the t 0 plus y0 times 0 e to the negative 2t. That's a linear combination of a couple column vectors. I've been trying to hit home in your brain that when you have a linear combination of column vectors, that's the same as a matrix times a vector. That's the definition of a matrix times a vector. What matrix? The matrix where these vectors are its columns. E to the t 0 and 0 e to the negative 2t. And what vector? The vector whose components are the weights, x0, y0. This was not required as your CP here, by the way. I'm doing extra. And guess what? This thing is the matrix exponential of a coefficient matrix that I haven't specified yet, e to the capital A times t. And this thing is your initial condition vector, capital Y0. What is A? A is the coefficient matrix for the system if you wrote the system in vector form. Let's do that over here. In vector form, this system of two scalar differential equations is equivalent to one vector differential equation that you could write like that. But you could also write like this. And you could also write like this. And once again, we have a linear combination of column vectors. That's a matrix, 1, 0 in the first column, 0, -2 in the second column, times the vector xy. Yeah, that thing is your A, and this thing is your capital Y vector. That's the A, and there's its matrix exponential. To get from here to here, we keep the zeros as they are. For the numbers on the main diagonal from upper left to lower right, we make them the coefficients of t in these powers of e. In this case, because the matrix is diagonal, that doesn't work in general if the matrix is not diagonal. You can't jump to something so simple in general. That's why we need all of chapter 3 in the textbook, is because you can't do that simple translation of a diagonal matrix to its corresponding diagonal matrix exponential just by keeping the zeros as they are and taking the coefficients on the main diagonal and making them the coefficients of t in powers of e, 1 and -2. Can't do that in general, but you can for diagonal matrices. Diagonal matrices are special. You can for completely decoupled systems. Completely decoupled systems are special because they correspond to diagonal matrices. Question? Yep, diagonal matrix means the only non-zero numbers are on the main diagonal from upper left to lower right. That's a very special diagonal of the matrix. All the other numbers that are not on the main diagonal from upper left to lower right are zeros. And this applies to any dimensional square matrix. Got a 10 by 10 square matrix. It's going to be diagonal if the non-zero numbers are on the main diagonal and everything else is a zero. Actually, you can have zeros on the main diagonal as well. But the only possible non-zero numbers are in the main diagonal from upper left to lower right. The matrix exponential, again, is defined to be, by definition, this is a definition, it's defined by a power series. I mentioned this a week ago or so. That's analogous to the power series for e to the x from calculus 2. The power series for e to the x starts with the number 1. I'll write it over here. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. What's the matrix analog of this, where x, instead of being a number, is a matrix? Well, just replace all those x's with a times t in this case. That's acting like the x. And I guess the number 1 should get replaced with it by the identity matrix, because I, the identity matrix, acts like the number 1 for matrices. It's the multiplicative identity. I times any matrix is that matrix. For the 2 by 2 case, this is 1, 0, 0, 1. Replace all those x's with a times t. I'll put the factorials in front. A is a matrix, t is a scalar. A times t is a scalar times a matrix. Typically, we actually put the scalar in front. So AT more typically should be written as TA. To multiply a scalar times a matrix, you multiply every entry of the matrix by that scalar. I'm not proving that this is going to give you that. If you tried working it out, you would, I hope, at some point with enough time, believe it. It's probably too time consuming for us at the moment. But it does equal this. This is the definition, and you could, for the diagonal case, calculate this fairly easily compared to a non-diagonal case. Change of variables, skew coordinates, geometrically are about changing the location of the axes. Algebraically, they're about making this calculation possible to do in a reasonable manner. Say that again. I'm saying one of the most important things of the entire semester right there. Change of coordinates, skew coordinates, geometrically corresponding to changing where your axes are. It's done so that this kind of calculation is easier to do. That's the purpose, including in the non-diagonal case. And in fact, well, it will even do it here still today before we're done, with maybe technology to help a bit. And this is what I call the beautiful generalization. The fact that the solution y equals capital phi of t equals this perfectly generalizes the scalar case. I think it's so beautiful. I call it the beautiful generalization. If you ever hear me saying the beautiful generalization, or if I ever put it on the test, what is the beautiful generalization? That's what it is that this matrix differential equation, dy dt equals a times y, based on a certain vector initial condition, that's you're imagining to be specific, has a unique solution. This function equals this. Again, it perfectly generalizes to the matrix situation what we've known since lecture 1 for scalar equations. The unique solution to that scalar initial value problem is y equals y0 e to the at, which I could also write as e to the at times y0. Matching that. That's the vector form of that. Beautiful. But that works. That's my name, the beautiful generalization. Okay, so you only need to write this part. And by the way, if you didn't use the capital phi notation, that's okay. I'm not expecting that. You should feel comfortable when I use it. And if I do allude to this on exam 3, which I will with flows, you should be able to handle it. I'm not going to talk about flows for the moment, but let's talk about number 2, sketch the phase portrait. So for the phase portrait, again, we're thinking about dx dt equals x, dy dt equals negative 2y. We got to think about nullclines. I'm trying to draw these phase portraits typically without bothering to draw the vector field. I saw some of you drew the vectors in the vector field, and that's fine, but that seems like too time consuming in my mind. So I'd prefer just sketching solutions based on nullclines. The x nullcline is where dx dt is 0. But for this example, that's equivalent, look at the right-hand side, to x being 0, which is the y-axis, the vertical axis. The vertical axis, the y-axis, is where the vector field has vectors that are pointing either straight up or straight down. In other words, the vertical axis has to be a straight line solution. That's not typical, but it does happen here. And likewise, the y nullcline is the horizontal axis. In general, that's where dy dt is 0. which in this case is equivalent to negative 2y equals 0. In other words, y itself equals 0, which is the x-axis. There, the vector field has vectors that point horizontal. Their second component is 0. They're either pointing to the right or to the left. And since the x-axis itself is already horizontal, solutions have to be on that. They don't cross it. They're straight line solutions. You could think about that with the formula as well. If you start on the y-axis, up and down, where the initial value of x is 0, the first component is going to go away. 0. You get 0 for the first component and an exponential decay for the second component, which goes to 0 as t goes to infinity. In the y direction, the origin is going to be a sink. The arrows will point toward the origin. On the other hand, if you're on the horizontal x-axis where y is 0, this one's 0. And your solutions are this thing 0. That goes away from 0 as t goes to infinity. It grows. So in the horizontal direction, the origin is a source. Where x and y nullcline intersect, you have equilibrium points. They only intersect at the origin. The origin's your only equilibrium point. That's typical for linear systems. There ever a time where there's more than just the origin as an equilibrium point? Yeah. The determinant of your coefficient matrix would have to be 0 for that to happen, though. It would have to be a non-invertible matrix. With a kernel that's non-trivial as a linear transformation. Our matrix here, A, has a determinant of -2. It's diagonal. Multiply the numbers in the main diagonal. Not 0, it's invertible. The corresponding kernel is just trivial, just the 0 vector, just like the origin is the only equilibrium point. I said in the y direction, solutions head toward the origin, and the x direction, solutions head away from the origin. So in some sense, the origin is a sink in the y direction and a source in the x direction. Overall, though, what do we call it? A node? Does anybody read ahead enough to know what to call this? Read ahead in the book or watch the videos ahead. We don't call it a node in 2 dimensions. It's related to horseback riding. It's a saddle point. Yeah. What do the other solutions look like? This is where you could use your calculator in parametric mode. They look like this. They kind of got to follow those other arrows. How would you know that? You could test points in the different coordinates, in the different quadrants, and see where dx dt is positive or negative, dy or dy dt is positive or negative. Pretty easy to think about here. Dx dt is positive exactly when x is positive. And dy dt is positive exactly when y is negative. Solutions are going to move to the right over here when x is positive, first and fourth quadrants. Yeah, they're moving to the right as t increases. And they move to the left over here where x is negative. Again, dy dt is positive when y is negative. Down here, solutions go upwards, this way or this way, where y is negative. And dy dt is negative when y is positive. Solutions are going down. Yes, you could draw the vector field. Like if this is the point, that's the point 1, 2, say, or as a column vector, 1, 2. If you plug that in the vector field, the right-hand side of the differential equations, you get an output of 1, -4, actually. Right? -2 times 2. Plug this in the vector field, call it capital F. Meaning in this case, to multiply the matrix A times 1, 2, the matrix A was 1, 0, 0, -2. Multiply that by 1, 2, you get the vector 1, -4. If you plot that in the vector field as an arrow, it's got a horizontal component of 1 and a vertical component of -4. If I drew it at the correct length, it's going to look something like this. The solution, a solution going through that point at a certain moment in time has to be tangent to that. Say maybe about like that. When you use Mathematica vector plot, it shortens all the vectors in the vector field to make the picture easier to interpret. But in reality, the vector field consists of longer vectors, typically. And stream plot gives you pretty quick plots of many solutions. But you should be able to handle doing this without technology. In general, what happens to solutions? For most solutions, x goes to plus or minus infinity, and y goes to 0. Are there any solutions where that doesn't happen? Well, along the y-axis, y still goes to 0, but x stays at 0. Your straight line solutions are those ones along the axes in this case. They are solutions as parametric curves. They're straight lines. We call those straight line solutions. Those would be the straight line solutions, and that would be part 3. Can I clarify anything? What's the flow idea? And the flow idea is to take this equation essentially here and the equality there as well, and just change your perspective. That's all it is. It's just a change in perspective that turns out to be useful in certain places in chapter 3, and also especially in chapter 5, it'll be useful. Here we're thinking of x0 and y0, or vector y0, as fixed, constant vector, and t is the variable. The flow just changes the perspective and says, think of t as constant and x0 and y0 as the variables. And to do that, I use a different notation. In the vector case, I don't think I typically use the curvy phi. I have to look and double check that. I think I still use the capital phi. To double check that. I haven't looked at it recently. But I make the t a superscript and the y0 the variable inside parentheses. It's the flow. In reality, when you think of t as the variable and y0 is fixed, this is a function of t, but it's a family of functions, one function for each initial condition. Here, this is a family of functions as well. One function for each value of t. Whereas this function is a parametric curve that's not a linear function of t. This, for a fixed t, is a linear function of y0. It's this matrix, the matrix exponential times y0. That's a linear transformation. And a big part of the point of talking about this is to relate differential equations to difference equations. If I pick this especially nice time, t equals 1, I consider what's called the time 1 map. Capital phi superscript 1 of y0 by the beautiful generalization. Its formula is exactly this, where you replace t with 1. You get the matrix exponential of just a by itself, times 1, times the vector y0. That's called the time 1 map. And you can think of this as generating a difference equation. Using subscripts n and n minus 1, I could write vector y sub n equals the time 1 map of vector y sub n minus 1. Don't let it bother you that I've changed the y0 to a yn and a yn minus 1. It's not a big deal. It's just a symbol. Actually, to tell you the truth, when you read books about this stuff, they typically don't even put the subscript of 0 there. They just call it a y. In other words, we're doing e to the a times y sub n minus 1. And what's the connection between solutions of the differential equation and solutions of the difference equation? The connection is that yn, the solution of the difference equation, is the same as the solution of the differential equation based on the initial condition y0 when you plug in time n. And if you look at that fact in the context of a linear example like this, it's like, well, what else could it be? Yeah, I mean, if I replace t with n here, I'm going to get the exact same thing. It's the exact same formula. What else could it be? But the point about the flow idea here is that this works even with nonlinear equations. Catching what I'm saying here? This fact here works even with nonlinear equations, as long as they're an autonomous system. But the catch is there's no more matrix exponential. So it's simplest with linear systems. You can only do the matrix exponential if you've got a matrix A. In other words, only if the original system is linear. But the flow idea, the time one map and the flow idea and this equality works even for non-autonomous equations when they are even nonlinear. You might not be able to find a formula for the time one map, but you might be able to approximate it for nonlinear systems. By the way, you might have wondered, do flows have any relationship to fluid mechanics? The answer is yes, they do. And that's why they're called flows. So if you're in fluid mechanics, what you're doing is actually more complicated in reality than what we're doing here, but they are related.